Good morning, everyone, and welcome to our Friday seminar, so our last seminar for this semester. And we're delighted to have with us today a very special guest, Professor Jerome Reiter or Jerry Reiter from Duke University as our speaker today. Jerry is a professor and also the department chair at the Department of Statistical Sciences at Duke. And Jerry has done a whole lot of work, it goes without saying, in various kinds of areas and leading to loads and loads of publications. But his main research interests are in 3 or 4 different areas: missing data, measurement error, methods for ensuring data privacy, and data integration methods, and also analyzing complex data in social studies and public policies, if I remember correctly. And he has a long and illustrious profile, so I'm not going to go into all those details, but he's a fellow of the ASA, he's a fellow of the IMS, and he's also received many awards, distinguished awards for teaching and mentoring at Duke, including undergraduate teaching awards, postdoctoral mentorship awards, and also data science, Master of Data Science Distinguished Fellow Award. And he's going to tell us today about some of his recent interesting work on how to handle so-called non-ignorable missing data problems when you have auxiliary information available. So please join me in welcoming Jerry.
Thank you, Abhishek, for that kind introduction. Thank you for the invitation. It's great to be here, see a lot of friends and heroes. It's an honor to be here. I'm going to talk about some research that I've done with colleagues, Owen Raju Akande, who's a former PhD student of mine, Gabriel Mattson, a former political science PhD student, and Sunshine Hillegas, who's a political science faculty member at Duke. This is work that we were motivated with thinking about missing data in the current population survey, which is sort of I'll talk a little bit about it, but it's a really widely used survey. It's kind of the go-to survey that people interested in assessing whether voter turnout, for example, go to. And there's some missing data in it, and this issue of using auxiliary information to try to help you with missing data turned out to be a broader issue. And so I want to tell you about some of the ideas that we've looked into and are continuing to look into on this problem. Please feel free to ask me questions at any time. So let me start off with the motivation. Surveys are in trouble, right? There's increasing rates of non-response, both for item non-response and unit non-response. And at the same time, there's less and less resources that survey organizations have to try to deal with the non-response, to follow up people or individuals for non-response. And so it puts these organizations in the position where if they want to deal with the missing data, they have to make very strong assumptions, right? The most common assumption that probably a lot of you have made is a missing at random kind of assumption, right? The data are missing because of other variables. They're not missing because of the values themselves. Or some kind of not missing at random model where you posit a very specific, say, a selection model, that says, oh, the probability of missing depends on all these variables, including the variable that's missing, like a non-ignorable selection model. Okay, and of course, the difficulty here is that it's really hard to tell if those assumptions are good. The data are missing, right? That's the hard part of this whole game. And they could be unrealistic, particularly the missing at random models that we all go to kind of by default. And so at the same time as this problem, we also have this wonderful revolution in data availability, right? A big data, organic data, found data, whatever you want to call it. And in social sciences and policy, the areas that I tend to work in, there is this information that can come from, for example, censuses or administrative databases, or perhaps private sector data aggregators that have all this stuff on us, right? And so It would be nice if we could think about how we can use that information, perhaps to help us maybe weaken or reduce the reliance, the strength of some of these missing data assumptions that organizations are forced to make. So let me just give you like a very simple illustration just to hopefully convince you that using some of this auxiliary information might be able to help us do a better job. Let's take the simplest kind of example possible, right? So we did a simple random sample, and the only question we're asking is sex, okay? And let's suppose that it's got some item non-responsive. And it happens to be that 70% of our respondents report female, okay? Now, let's suppose that in this population, we know that around 50% should be female, 50% male. There's some others as well. Let's say that that's a small fraction. So it's roughly 50% female and 50% male. Okay. So if we're going to impute, or we're going to fill in these missing sex values, we know that we should be imputing more male than female to try to get that imputed margin closer to the target population. And it just makes sense to use that marginal auxiliary margin to get us there. Well, if we didn't use that margin, if we just did like a missing at random kind of model, then basically you would be imputing the missing sexes using the data we have. We're making it look like the data we have. We basically would be imputing 70% female for those missing cases as well, and that things would be off. So this is just a little story to try to convince you that if we can have these auxiliary margins from these external sources, we might be able to use them to do a better job at handling potentially non-ignorable missing data. Okay. Well, let's generalize this idea. So this is the setting that I want to work in. We have an organization, I'm going to call them agencies. I work mostly with federal agencies, government agencies, but think of it as any survey organization. And they have accurate estimates of population percentages. I'm going to work with percentages, categorical variables in this data set. Okay, for some of the variables in the survey, not necessarily for all of them. We have these rich surveys, but we might know some population margins, some population percentages from external databases. And I am talking about margins here. I'm not talking about knowing data on individuals. That's a whole other problem, which is really important as well. But here I'm just saying I know certain margins, certain population percentages. They might be univariate, they might be bivariate, more. That's the context. Okay, so I want to use those margins, those auxiliary information, to try to do a better job at handling the missing data. And I'm going to think both about unit and item non-response. Okay, so in fact, what I'm really going to try to do is try to help use those margins potentially to do things like, well, maybe there's a non-ignorable model, a not missing at random model for a unit non-response, and maybe I'll allow myself like more of a missing at random type model for item non-response, or vice versa, right? So I want to be able to handle the missing data differently and try to use that margin if I can. Now, of course, this is not a new scenario. Those of you who are familiar with government agencies in particular, you know that they're using auxiliary information all the time, right? So they know population totals, and they'll adjust survey weights or things like that using post-stratification adjustments to try to make their weighted estimates match the population totals. Okay, so it's not really a new situation, but I'm really going to do this in the context of modeling and imputation as opposed to survey weight adjustment. I don't see this idea of using these margins really affecting the way the agencies handle item non-response imputations, for example. Right? They'll often just bump up weights for unit non-response. Okay? So that's the goal, right? What we want to do is develop a framework to try to leverage these population-based auxiliary margins to, one, allow for more flexible modeling and potentially non-ignorable non-response mechanisms. Two, we want to handle both item and unit non-response, right? And three, potentially handle them differently, right? Have different missingness mechanisms for the different types. Okay, and I'm going to today talk about using Bayesian modeling, or in its cousin, multiple imputation for missing data to propagate the uncertainty from doing those imputations. Okay, so that's the big picture goal. Okay, let me start off, the obligatory notation slide, but let's start off there. I'm going to use D for the data that we have and A for the margins. Remember, A are just going to be population percentages. Okay, I'm going to have X represent variables that we have margins for, basically, and Y are the other variables that we don't have margins for in our survey, right? So you might be thinking about X might be demographic variables or something like that. We need non-response indicators. So we're going to have unit non-response and item non-response. Unit non-response is that an individual didn't respond to your questionnaire at all. They gave you nothing, basically. Item non-response is they filled out some things, but not others. So U equals 1 if the unit non-responder and 0 otherwise. Then I'm going to have R's be 1s if they are an item non-responder to a particular variable and 0s otherwise. So that's what the RI. I've got super X's just to indicate it's an X, one of the X variables, and super Y's to indicate it's one of the Y variables. But the R's are going to be item non-response indicators. Okay, so I have data and I have these indicators that are floating around as well. Okay, here's the general idea. We call it the missing data with auxiliary margins framework. Basically, it's going to work as follows. Big picture. The big picture is that we are going to build a joint distribution for all those variables that I listed on the last 2 slides. Okay, and I'm going to do that by building a sequential factorization. You don't have to, but this is kind of the way that I find a little easier. But basically, variable model for variable 1, the model for variable 2 given variable 1, variable 3 given variable 2, variable 1, etc. Okay, so a sequential factorization to build up that joint distribution. And what I'm going to do is use the margins that I have to help me decide how to build that joint distribution. In particular, I'm going to use the margins, as you'll see, to help me build models for the U's and the R's. Okay. I'm going to require the models to be identifiable. I'm not going to talk a whole lot about that, to be honest. There's a paper that I wrote with my another former postdoc, Mauricio Sadinle, that talks about identification of the kinds of models that I'm going to present to you today. But I'm not going to get into the math on that. But basically, I think of identification the way you normally do, and we want those to be identifiable. So we don't want to put in parameters there that basically you can't estimate. And what we're going to do is sort of do this in 2 steps. Okay, step 1, we're going to basically specify a model for the observed data, for the D. Okay, and that model is pretty much going to be an identifiable model. That's one we should be able to estimate without the margins, without these auxiliary margins. Okay, and you'll see just some simple examples, and you'll see that it's kind of what you might just naturally do, right? Build models. There are generally default models for handling the non-response, like a missing at random model, for example. Okay, start there. I'm going to do selection model specifications. That is, I'm going to model the X's and the Y's first, and then the R's and the U's given the X's and the Y's. But you could flip it. You could do what's called a pattern mixture model specification, where you model the R's and the U's first, and then the X's and the Y's given the R's and the U's. But I'm doing a selection model in this presentation. Okay, other stuff we've been doing pattern mixture models. Okay, so that's step 1. Basically, model the data the way you normally would, without thinking about the margins. That's step 1. Step 2 is incorporate the margins. Okay, and basically what the margins are going to do is they're going to give us additional constraints on the joint distribution that we can turn into additional parameters that we can estimate in the models. Okay, and so really that's what I'm going to wind up doing. I'm going to basically add parameters to the models from step one to try to weaken the assumptions that I've made in step one, right? And they've got to be estimable parameters. Typically, there's many ways that you can do that, multiple ways that you can do that, and depending on what A looks like. And so what do? Well, okay, you can pick some that seem to make scientific sense, talk to your domain scientist collaborators or political scientists, but you don't have to pick one, right? You could, with all missing data, the right thing to do is some kind of sensitivity analysis where you might try different kinds of model specifications and see if your results are particularly sensitive to them, and if so, then be honest about that, right? So that's the MDAN framework, right? Specify models, add parameters based on what margins you have. So let's see how this works. Let's take a really simple example to get us started. Okay, the easiest example we can imagine, right? So two binary variables. Right? So no unit non-response, just item non-response in X1. X2 is completely observed. So that's what the little picture is showing. Question marks are missing, check marks are observed. Okay, I have the margin for X1, but I don't have the margin for Y1. Right? So that's really what the data look like. You notice I have a question mark there for response for the auxiliary margins. Basically, I don't have that margin. Well, never mind. I'm gonna scratch that sentence because I've started thinking about actually having data. But what I mean for this is that this is a margin. I don't want this to look at this as data. Right? Think of this as just a margin on X1. Right? That's all I have. Okay, so this is as simple as we can imagine a data set being. So what can we do? Well, MDAN framework, first step, we'll specify some model for the observed data. And really this could be, well, a model for the X's and the Y's. Well, this is a two binary variables. So it could be a multinomial, or it could be a binomial followed by a logistic regression or conditional probability, given the first one, the Y given X. Right, so we're going to specify that model, and then the second model is the R model, the model for the non-response, and I've written that in generic notation too. But basically, think of that as like a logistic regression, if you will, some binary regression that predicts whether somebody responds to X or not. And the key thing is that I'm using Y, and that's it. I'm not using X. That's missing at random. Right, the reason why X is missing depends on Y, which I fully observe, but it doesn't depend on X. Okay, so I've started there. That's my step one. That's kind of naturally what you might do without the margins. But now I get a margin, right? So I know the marginal probability of X1. So that gives me one more piece of information, right? One more constraint on this joint distribution for R, X, and Y. Okay. And so I can add one more parameter to this. Well, okay, really the only place I can add that parameter is in the model for R. And I'm going to do that by adding a main effect for X1 into that equation 3. Okay. That's identifiable. Okay. That model is it's called an additive non-ignorable model. It's not, I didn't create that model. That's a model that was proposed by Imbens and Rubin. They have a paper in 2001 that talks about additive non-ignorable models in the context, not of auxiliary margins, but in the context of longitudinal studies where you have a new sample at a later wave called a refreshment sample that you take, and you could basically build this kind of model to analyze that kind of data. But the cool thing about equation 3 is compared to equation 2, right? That's our missing this mechanism, is that it's a more general model, 3 as compared to 2. Right? So in fact, 3 encapsulates 2, right? 2 is a special case. If the data, if eta 2 in front of X1, if that's 0, then we have a missing at random. Okay. If eta 2 is not 0, we have a not missing at random model. So in some sense, we can let the data decide if it's missing at random or not missing at random, at least a particular kind of not missing at random, right? I should say, well, there's clearly still an assumption in here, right? I didn't avoid assumptions, right? The assumption you probably see it, that I don't have an interaction between x1 and y1 in that equation 3. I can't identify that. I don't have enough. If I had xy margin, I could identify that, but just the margin of x alone, I can't identify that. So that's why it's called the additive non-ignorable model. There's no free lunch with missing data. You've got to make some kinds of assumptions, but we've weakened the assumption in 3 compared to 2. That's what we're trying to do. Okay. Please,
are you making any kind of an assumption about x1 given y1's distribution here, right? Because the first model also has given x1, y1, and second model, like 2 and 3, I mean, both have x1, y1 condition, and then somehow you're saying that knowing the marginal of x helps me, so basically make this model identifiable. The third one, somewhere, everywhere, there is a conditioning involved in the y.
Yeah, I see your point. So I am actually, you're right. You could try to embed that in there, but I'm letting x and y kind of roam free. I'm just letting that be, let's say, a multinomial, if you will, and then I'm letting the margin for x come in through that equation 3. Okay, so you're right. I'm not using that piece of information when I'm specifying 1. Okay, but that would make it more complicated.
And when you say you know the marginals, it's generally, you mean that I know the distribution of x essentially, right? A particular. So I'm trying to say, like you said, that I know the percentage, but that typically applies when it's a binary or a categorical out, like a variable. But your x could be continuous?
Yeah, so the question was about continuous versus categorical. So I am assuming categorical here. I'm not doing this for continuous. It gets a little trickier with continuous. A lot of the marginal information is categorical. Demographics. You'll see with the voting example, we know the number of people that voted in the election. So there's a margin there. Okay, yeah. Okay. Right. So this summarizes what we talked about in terms of this model 3 being more general. Okay. And that we basically weaken reliance on these assumptions compared to equation 2. Right, so we've talked about this slide, but the basic idea is that second bullet. Really, for each variable we have a margin, we're going to be able to add one more term. Okay, that's kind of the idea in a nutshell. Right, and so where we put that parameter for that term, I mean, that's up to us. Well, there are constraints on that because we want it to be identifiable, but given that, there are going to be multiple options for where we could put it. Okay, let's get a little more complicated. Yes?
Just a quick question. Say if you have x1, x2, and they have some missingness, you have the margin. Can you add, I guess you can add x1, x2 as main effects. Can you also add the interaction on top of it?
So the question was, if I understood, if I have, well, in this notation, if I have x and y, and I have the margin, the xy margin, right, together. If I have xy margin, then I can, in fact, add that interaction to equation 3.
What if you have just two x1, x2?
If you have the two margins by themselves without the joint, no, you can't.
No, I'm saying if you have x1 and x2, in addition to y1. So let's say you have a y1, x1, x2.
Oh, you're asking, could you?
And you have margin for, let's say, joint margin of x2, x1.
Yeah.
Can you? I'm pretty sure you can add x1, x2.
Yes.
As a main effect.
Yes.
But what about their interaction?
Yes.
You cannot. Okay.
Yes.
Don't you need the joint of x1, x2?
That's what he said we have.
Joint margin. If you have joint margin.
Yeah.
Oh, I see. Yeah.
Without the joint margin, there's just two main effects. That's right. Okay, let's step up a little bit more on complexity now. Okay, so building up a little bit here. Okay, again, let's stick with the binary variables, but now let's add unit non-response, and let's let both of them be subject to item non-response. Okay, this is starting to get a little more like what we see. Of course, it's not a lot of variables here, but this is the kind of ugly patterns that you wind up seeing in this contingency table that would describe the joint distribution, right? So we know whether someone responded or not to the survey. So we have U, we have the item non-response indicators, we have the R's, right? And we have X, we have X1 and X2 for people that responded to both, but we only have X2 for some and X1 for others, right? So we have this kind of Swiss cheese pattern, and I'm going to assume we have the univariate margins for X1 and X2 in this problem. Okay. So, okay, this is 2 to the 5th, right? Cells in this contingency table, if we expanded it all out, so it's 32 total probabilities that we need to come up with. Of course, they sum to 1, so really 31 probabilities we need to come up with. We do not have 31 pieces of information in that little table, right? I mean, you can see, what do we have? Well, we have the marginal distribution of U, right? We have that, so that's good. We have a conditional distribution of R2 given U equals 0. That's another piece. We have R1 given R2 equals 0, U equals 0. R1 given R2 equals 1, U equals 0. You can see that we have pieces, right? In fact, if you kind of work your way through all the pieces, you will see that we pretty much have 8 pieces of information. Okay, and this is, the notation here is a little bit messy, but if you work your way up, I guess, you would see that the P is the probability U equals 1, then I have S's for those probabilities for R1s, Q's, working your way all the way up to all these conditional probabilities that you can observe. If you just track along the U equals 0 and R equals 0 cells, you'll get all of these probabilities. Okay. So that's it. So you have those 8 parameters, but there's 31 that you need plus the sum to 1 constraint. So we can't get anywhere close to fully parameterizing this joint distribution of this table. But the margins give us 2 more parameters, right? They get two more pieces of information, 2 more constraints on the probabilities, which then we can translate into 2 more parameters. So let's try the MDAM framework. So let's start with our default, right? So our default model, again, will be this distribution for X, which, you know, multinomial or something. Then I'm going to have a model for U. My default model for U is going to be basically, this is a missing completely at random model. That's what 5 is. Right, that the reason for missing is it's some function of an A to 0. It's totally unrelated to any of the other parameters. Okay, so that's a default thing. We really can't do anything else, be identifiable. And then I'm going to basically in 6 and 7. You'll notice 6 and 7 that those are special. Those are what we've called item-wise conditionally independent mechanisms. That there's a reason that R1 is missing, could depend on X2, which, by the way, can be missing. So that's why it's not a missing at random model. That's why we called it item-wise conditionally independent. But it doesn't. But missing this for R1 doesn't depend on X1. Missing this for R2 could depend on X1, but it doesn't depend on X2. Okay, so that's what we call item-wise conditionally independent. Mauricio and I wrote about that in 2017. So this is an identifiable model. If you count the number of parameters, you'll see that there are just as many parameters as we have pieces of information. Okay, and we have the theorems in the papers that say it's identifiable. Okay, so but this is very strong, right? And we'd like to use this auxiliary information. So what does the auxiliary information give us? Well, we've got 2 parameters. So what are our options? Okay, one option is we could basically add a parameter to the unit non-response model, right? So we could take, or add 2 parameters, I should say. Add 2 parameters to the unit non-response model. Take 5, leave 6 and 7 alone. Leave item non-response to be ISIN, but make unit non-response essentially that additive non-ignorable model. Okay, so that would lead to 8. That's one option. Okay, Or we could leave unit non-response missing completely at random. We could leave 5 the way it is. And for 6 and 7, we can add x1, a term for x1 to 6 and a term for x2 to 7. So make the additive non-ignorable for the item non-response. Okay, like I said, there's, and you can imagine as you start to grow the number of variables, the number of margins, you have a lot of options, which is a practical challenge. Okay, so that, I mean, you could do one for unit and one for item, I suppose, if you wanted. So there's lots of flexibility here in the way you could use this auxiliary information. So what do you do? Well, so really the way we like to think about it is basically when you're getting that margin, you're able to encode a relationship between that variable and some non-response indicator. Right? That's what it's going to allow you to do. And the question is, do you want it to be for the unit non-response or the item non-response? Okay. And so, well, the way I like to think about that is, think about the problem that you have. So suppose you have a data set where you have a lot of unit non-response and not so much item non-response. In some sense, whatever you do to the item non-response model doesn't really matter that much, right? If you have like 2% item non-response, who cares, what you really do to it? Probably. I mean, okay, you can have extreme cases where it might matter, but in general, whatever you do there, as long as you're half decent, you're probably going to do okay. But if you have a lot of 30-40% unit non-response, you might really want to dedicate that flexibility to the U model and give it up on the R model. And it could be vice versa. If you really were worried that item non-response was not ignorable, people weren't telling you the answer because of the value, because they were a 1. But unit non-response, either you didn't have that much or you weren't, you're not that worried about it. Maybe from past experience, that they're not that different. Then dedicate it to the R model, right? And of course, you don't have to choose one or the other. The whole idea is you could try both models and see what kind of results come out and if it changes your overall conclusions. Okay, so that is the idea. So let's do our application to voter turnout, the CPS. Okay. The reason why the political scientists really like the CPS is because, one, compared to a lot of surveys, actually the non-response rates are not as brutal, but also it drills down. So it asks a lot of questions, and it gets really detailed questions on items like race, for example, and so they like to use the CPS to estimate voter turnout. Okay, what's the probability that somebody turned out to vote given their characteristics? That's the question they want to ask. Okay, so here's the missing data rates in 4 southern states that are in my area of the country, sort of. And you can see actually that, well, I mean, look at the middle one, look at sex. There's like basically no missing item non-response in the sex. There were 2 people, I think, or 7 in the whole 4 states where there was missing sex values. So that's good. We don't worry about that. Age is very low non-response. Age, by the way, is going to be a bucketed variable. It's going to be a categorical variable. That's how CPS gave it in the data. So that's 3, 4, 5%. Not a huge deal. Vote, that's really the interesting one, right? That's what we care about. Did you vote or not? So a lot of people are not answering that question, but they're answering other stuff. But they're all much smaller compared to the number of units that don't respond. Right? There you're talking 20% and up. Right? So a lot of people just aren't responding to the survey entirely. Okay, and so we want to deal with that. We don't want to totally ignore it because maybe maybe it's not missing at random. Maybe the reasons for missing this are not ignorable. So let's start trying the MDM framework for this. Okay. So by the way, of course, the Census Bureau worries about the missing data. It's not like they close their eyes to it, and so they do stuff. What do they do? Well, for the unit non-response, they re-weight. They change the survey weights. They basically up-weight the respondents. That's what government agencies do pretty much universally when it comes to unit non-response. They upweight. Okay, we're going to impute. And then for item non-response, they make this I mean, this kind of really funny assumption here. Basically, anyone who did not respond on the vote, they count as someone who did not vote. Okay, so they're basically doing a non-ignorable missing data model, and a very, very strong one. Okay, and you'll see why they do that in a second. So that's what they do. And now, if you go analyze the Census Bureau public use file for CPS with the voter supplement, you'll be basically analyzing data where they've done those two things. Okay, we had to undo them for our data. There's other folks that have suggested things. So there's one that I thought was interesting, is Her and Atchin. What they did is they said, okay, let's just throw away everyone who's a unit an item non-respondent on vote. Just throw them out, which right away, if you're a missing data person, you're throwing away a lot of partially observed information, which is unfortunate, but that's what they did, or recommend, I should say. And then they re-weight the remaining observations, the ones which all were observed, by essentially taking the true turnout, because we know the true turnout after the election's over. These are presidential elections. After it's over, we know how many people actually voted. So we have the margin. Okay, that's the margin. That's what that's what inspired us. And they just upweight all the survey weights of the respondents. Okay. But again, they're throwing away a lot of this partial information by doing this. Okay, and so I don't want to throw away, all that. I mean, it's not a lot in this one, but there's still 20. Well, could be up to 25% of the data, but I mean, it's probably less, but could be. Right. Okay, so let's do the MDAM. Oh, we're going to give you a little more of the data first. Sorry. This is why the Census Bureau does what it does. Okay, so if you actually look at the turnout in the complete cases, the people who actually responded, unweighted estimates, look at those percentages. In Florida, apparently 75% of the people say that they voted. It's the measurement error that I was alluding to, right? In North Carolina, home state, 77% of the people say that they voted. If you know anything about U.S. elections, unfortunately and very sadly, we do not get 77% of the people voting, even in presidential elections. This is 2012. I forgot to mention that. So it was it was a popular election, right? The actual turnout, the actual margins are available from federal election statistics. So we know those margins. 64.8 in North Carolina, a lot less than 77, a lot less. Okay, so perhaps this is an indicator that this missing data is not ignorable. Maybe the people that didn't tell you about voting or didn't respond at all are the people that didn't vote. Okay, social desirability bias built in, maybe. So we wanted to worry about that. We also have auxiliary margins for age by state from the 2010 census, so we adjusted it all to make sure we had a voting eligible population. Okay, let's write down the model and I'll show you the results. So the state, we have, these are the variables: state, sex, age. You can see age is bucketed into 4 categories: vote, did not vote, and then response indicators for each one of those. The model for sex is a logistic regression on state. We're just going to, state is our first variable. We assume that's known for everybody. Build it all the way up. Age, order of logit on main effects for state and sex. Vote model is a logistic regression on main effects for sex, age, and state, and then interactions of state and age. We looked at other interactions, other richer models, and these seem basically to predict the observed data pretty well. So we just, for simplicity, kept the models from growing, but you could add more richness. This is really the key action, right? So the MDAM framework, that's step 1. Step 2 is allocating these margins, right? So the first step model, you can see everything that's not in red is the first step model. Basically, we're gonna wind up fitting these kinds of models that I showed a few slides ago for unit non-response, the default model is just a regression on state. State's fully observed for everybody, so we can do that. Okay. For sex, we just do a regression on state. We could do more. This is the item non-response model for sex. We could do more, but there's only 7 missing values for sex, so we were just like, let's just make life easy. Fewer parameters to estimate. 7 values, who cares? And then these ISIN models, the age non-response indicator, item non-response indicator has main effects for everything except age. The vote non-response indicator has main effects for everything except vote. Again, in the stage 1 of the MDAM. Now we get the margins, right? So we have the age margin from the census. What are we going to do? Well, we have a choice. We could add it to the RA model, or we can add it to the U model. Remember, the item non-response in age was like 3%, 4%. I'm not too worried about that. So I'm going to add that age to the unit non-response model. I want to make sure that maybe my unit non-response depended on age, different by age. So I'm going to enrich in that model. The vote is more complicated because we had 25-ish% unit non-response, but we also had 15, 16% item non-response for vote. So you could argue either way. So we'll try them both. In this one, I've got it in the item non-response model, but you could still add to the unit non-response model. And I'm going to show you the results for both of those models. All right. So that's the idea. So let's see some results. Non-informative priors, using an MCMC, and the way we actually incorporate this marginal information is kind of a little cute little trick, which again is not really something that I feel that I've created. It's out there, but just adding pseudo observations to the bottom of the data file that represent the margin. So if we want to say that 65% of people voted in North Carolina, just add a large number of pseudo observations with this have vote. There's 65% voted, and that kind of that basically acts like prior information and pulls the model there. So we talked about that in this paper here for latent class models, mixture models, but that's the idea there. Okay, so first thing I want to show you is some predicted turnout. So these are the 2 models. So this is predicted turnout among item non-respondents for the model that puts vote in the R. You can see basically what it does is it basically says everybody who is an item non-respondent in vote is a non-voter. That's exactly what the Census Bureau does, pretty much, right? So the Census Bureau is kind of implicitly doing an MDR kind of model. Whereas if you look at the unit non-respondents in that model where you stuck vote in the R, you can see that their voting percentages are sort of much more in line with what the respondents. This makes sense. Right? I mean, that's what the model says. The unit non-respondents look like the item non-respondents. Sorry, look like the item. Unit non-respondents look like the unit respondents, right? So that's why the percentages are roughly there. Whereas if I stick vote in the unit non-response model, now you can see that looking at the right panel, that unit non-respondents are much less likely to vote, right? That's what the model wants to do. I mean, it's basically, we're basically telling, when we put that parameter, is telling the model who is kind of eligible to kind of fix up the problem, the item non-response bias, if you will, okay? When we showed this to our political science colleague, she thought that this made more sense than the other one. But we've got both, and the question is how sensitive are results, right? So here's some results for population percentages. So remember, the true population margin in North Carolina is 64.8%. If you look at the complete cases all the way to the right, there's that 77% I mentioned for North Carolina, way off. Now we do this MDAM framework. Regardless of where you put the vote model, it's pulling that empirical margin really, really close to 65% where it should be. Okay, so that's what models designed to do. And the other things, other sort of subgroups, you can see there are some numbers there that probably are a little high in the complete cases, particularly like the less than 30-year-old voters, for example. 64% of them didn't vote. There's no way. the model is kind of pulling them back to something where our political scientists said they're more reasonable. Do I know these are correct? I don't, but they certainly seemed more reasonable to our political science colleagues. Okay, so the model is having the intended effect of moving away from, using auxiliary information to get better imputations. When our model checking, we basically do some posterior predictive intervals for all the observable joint probabilities in the table, all the two ways pretty much, and sorry, not the two ways, the four ways, and basically you compute posterior intervals, do that over and over and over. We get pretty much really good coverage of those observable quantities, 94%, 92%. Again, that's just a check if the model is capturing the observed data well. It doesn't tell us anything about if it's capturing the missing data well, but it's at least some assurance that what we're doing, the models we're writing down, at least are not very poorly capturing what the observed data look like. Okay. We did one evaluation, my second to last slide, one evaluation which we're able to do using, private sector data. So there's this company called Catalyst that collects voter registration data on all of us who are registered to vote. You're in there, I'm in there. Okay, they've got lots on us. This connects to my privacy worries, but they have lots of stuff on us. Okay, so what we can do is we can look at demographic characteristics of voters compared to the voter file maintained by Catalyst. So we can actually compare, right? We have those. And so what I'm plotting here for the two models is basically box plots of the differences for each state, differences across all those estimates that we have of the Catalyst percentage versus the percentage that we would predict from our model. And you can see that most of them are within a couple percent of zero, right? So that's an external validation that what we're doing, again, is somewhat reasonable. Okay, let me close with this slide here. Some of you may have been thinking in your head, well, in the CPS example, 77%, 65% is really far. Could that all be missing data? Probably not. There's published research out there, political science literature, that suggests that people overreport turnout. Right? They say that they voted when they really didn't. Okay, and so we want to incorporate that measurement error. And my PhD student Jerome is currently layering on a measurement error model using information from the political science literature to put a distribution on that measurement error, probability of that they misreported, if you will, and incorporate all of that into here and see what that does with the missing data and everything. Survey weights. So I didn't talk about survey weights at all. CPS has survey weights. Survey weights and Bayesian methods are really hard to bring together. Survey weighting analyses are done all the time. So the idea that we're doing here, we've been working on this, is essentially that when you do those imputations for the missing vote values, they have their survey weights attached to those. So when you do the imputations, try to do them in such a way that if you do what's called a Horvitz-Thompson estimate of a total, basically a survey weighted estimate of a total, if you've ever seen that, but that thing is plausible. When you fill stuff in, you do compute, pretend it's real data, and compute a Horvitz-Thompson estimate, a survey weighted estimate, you get something that's plausible compared to the true known total that you have, Tx. Where plausible is governed by that T hat X, that's the Horvitz-Thompson estimate, is approximately normal around the true total with some variance V that you get to pick to see how tight you want to be to that. So that's what my PhD students been playing with. We actually didn't get any for stratified sampling. There's a paper that just came out in a book that's That is a memoriam for Steve Feinberg. So that, and she's been doing it for basically unequal probability sampling, and it's working pretty well. So we're in the process of writing that up with the measurement error on top of it for this application. Higher dimensions, conceptually straightforward, but of course practically quite challenging. You know, when you have a lot of these margins, you have a lot of possibilities for how you could put them in, and you know, just thinking practically about that is something that we haven't done yet, and would require some, you know, definitely some domain knowledge to have any hope of writing down some useful models. But there's work to be done there. With that, I'll close up. I'll just flash up some references, and I'm happy to take some more questions.
Jerry, it was a very nice talk. I'm going to open this up to the audience.
I wonder, so in the CPS data, if you are missing completely at random, then how have you checked how the results change?
So if we assume, the question was, if we assume missing completely at random for CPS, how do the results change? Well, if we assume missing completely at random, then essentially we'd be using these complete cases results. Okay, and they are, as you can see, they're quite far from where they should be. They're far from our model, and they're far from, you know, that population margin. We don't have the margin broken out by groups, so we only have it for the, you know, the election is how many people voted. It doesn't say how many people that were of this type voted. But yeah, so that's what it would be. And a missing at random kind of thing, just running like mice or multiplication by chain equations or some other default package for missing data. It would give you very similar types of things as your complete cases. Mm-hmm.
Are there any other questions? Okay, well, if not, let's thank Jerry again.
Thank you.